So we are starting the today class, and we talk about data science and the way that we are considering the problem previous time. And we mentioned that, essentially you get the data, you need to clean it, and then you need to somehow see if everything is fine, maybe remove some of this noise from that. Then you will do some like machine learning on that, you make essentially sense of it, then you need to visualize it, and then you can communicate it. This is essentially the data science. Of course, this is a high level. We go to each of them in more details, and you will see that. But to do so, we need to have some tools. And some of the tools that we need, some of them are like some of the conceptual tools or fundamentals that we will talk about it, and we already mentioned that, for example, stats and other stuff. And some others would be some of the programs or the concepts and others that you need to know for this class. And then we want to go through this this week and the next week. So today, in particular, we are talking about this is like the introduction to probability theory. Then we talk about linear programming, introduction to graphs, and fundamental tools of data science in the later section. So introduction to probability theory. And first, we want to talk about some basics of probability theory, and then Bayes rules and the random variable and distributions. And that would be the things that we are talking about it. And hopefully, I want to have it. This is a crash course on probability theory, such that you know everything about it, because that's a very important one. Like all machine learning and other stuff cannot do it without this concept. And this is especially important for if you do interview in top companies, because generally they are asking, they want that you are quite aware of this kind of A/B testing, for example. And A/B testing is almost all of it is probability theory. You need to know, you need to have conditional probability and other stuff that we are talking here, and the different distribution, normal distribution, etc. So this is the very basic things, and it is good that you have a good understanding of that. So definition of probability. First, we define an experiment. What is an experiment? It's like you are tossed a coin twice. What are the sample space? So these are all possible outcomes of an experiment. For example, if you are tossed a coin twice, it is HH, HT, TH, or TT. What is an event? A subset of possible outcomes that you can have. For example, an event can be A equal to just HH, both of them comes head and head, or it can be B, HT, and TH. Probability of an event, a number which is assigned to an event, this is just some number, essentially, as long as it satisfies these three axioms. The first axiom, probability of A is between 0 and 1. All the probability should be 0 and 1. Probability of S, the sample space should be 1. Probability of empty set should be 0. That means that essentially, if you consider this whole sample space, one of them should happen. One of these events in sample space should happen, so the probability should be 1. Last but not least, he said that for two events A and B, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. And these are, note that A and B are the sets, so we can just define the union and intersection. Good. So here, anything that you will see essentially about probability theory should come out of these three axioms. Even the complicated stuff, all should be proved essentially via this. You may use some theorems, etc., but those theorems also have been obtained from these three simple things. Everything came from this. Let's see some examples here. The first one is that essentially the probability of not A is equal to 1 minus probability of A. And the second one is that for every sequence of disjoint events means that these are two sets which they don't have any intersection. That means disjoint. Probability of union of AIs. So this is also important. So what's the meaning of this? We are using it. So this means essentially all the AIs that we have. So in general, we have A1 to AN. These are the sets that we have. And then this means the union of all of them. Sometimes you will also write I equal to 1 to n. But if not, then it comes essentially even from the text. N is clear, then that means. So we have, this is the intersection. Also, we are using sigma the same way if you want to sum it up, or pi for multiplications. And in general, sigma and union are very similar to each other, and pi and intersection are very similar, as we will see. Here you will see that if you want to get probability of union of some events which are disjoints, then it is equal to just sum of the probabilities of individual events. Good. And here we want to just go through this and show how you can obtain this, and we can prove this stuff. So good. So here to prove the first one, essentially we can just use axiom 2 and 3. In particular, I can say this is A. Instead of B, I will say A bar. So I will put B equal to A bar, which is essentially corresponding to not of A. So in that case, then a probability of A union B would be essentially A, and A bar would be probability of S, which is equal to 1, according to axiom 2. And then it is with probability of A plus probability of A bar, or A tilde, minus probability of A intersection A bar, or A tilde. But A and A bar are disjoint. So this would be empty set, and then this probability would be 0. So then I have 1 equal to probability of A plus probability of A tilde, or not A. So then I can just essentially bring 1 minus probability of A here, and I have the formula there. So that's for the first one. What about for proposition 2? So we are thinking we have a set of disjoint events. So this is the time that I need to use induction. So induction, and there are induction and proof by contradiction, or proof by induction. These are two mathematical ways that you can do it. Again, you can go to my YouTube, Introduction to Algorithms. I'm talking about induction, several sessions of that. You can have a very good ideas about induction. And here, the idea is that in the induction, we have some basis of induction that say that, okay, this is correct for if you have only one set. So if you have only, so essentially we have this A1 to AN, and we want to prove it for them. So first we want to say that this is correct for n equal to 1. And of course, it is correct because here, this union would be just probability of A1, because we have only one set. And then in the other one also would be probability of A1. So this is correct. This is called basis of induction. So then we have induction hypothesis, IH. This means that it is correct, correct for n, we prove for n plus 1. So it means that it is correct from A1 to AN. Then I want to prove it for AN to AN plus 1. And how can we do that? So in that case, actually, again, we are doing this. So we are considering two sets. So here we have here we consider, so again, we are using axiom 3. For this guy, I will put it A equal to A1. For B, I will take essentially the union of I equal to 1 to n. Actually, I will use this one. So for this one, I'm using an plus 1 instead of A. So I will put A equal to an plus 1. And then for B, I will use it all A from 1 to n. Good. Now, if this is A, this is B, then I know that again, A union B would be the union that I want. That would be, so in this case, this would be equal to probability of AIs, I equal to 1 to n plus 1. Union of them. So this is the union of all these guys. This is the one that I have. So that, according to axiom 3, is equal to this. Now, I have here, it would be probability of AI plus 1, AN plus 1. What about the second part? What is the B? Then for B, I can use the induction hypothesis. I know that because it is the B probability of this union that is equal to probability of AIs, I equal to, so yeah, I equal to 1 to n. So here I'm using induction hypothesis. So I know that this is the probability of A n plus 1. Here, all I equal to 1 to n probability of A. So now when I add this one plus this one, then it would be equal to what? It would be I equal to 1 to n plus 1 probability of A. Good. Which is the so this is, I started from here and I ended here. So I say that these are, all of them are equality, so I have to do this. So this is essentially proof by induction. So I use induction and axiom 3. One other thing. There is a minus probability of A intersection B. Here, A intersection B, because these are disjoint, that would be empty set again, and then it would be 0. So I'm using axiom 2 here as well. So I'm using axiom 2, axiom 3, and induction hypothesis to prove it. So this was some good example that you can see essentially some of the way that we can formally prove this. And this is important. If we have a set of disjoint events, probability of union of them would be equal to probability, sum of the probabilities of individuals. And again, it is important. Union and sum play somehow similar roles. We will see that later. Intersection and multiplications or product would be the same. Good. So the one thing that we need a lot is joint probability. For events A and B, the joint probability, it is probability of AB or A intersection B, also known as, I mean, this is essentially AB or A intersection B. It stands for the probability that both events happen. So consider A equal to HH and B equal to HT and TH. What is the joint probability of AB? It would be 0 because A and B, they don't have any intersection. And the empty set probability of empty set would be 0. This is the concept of independence. We say that two events A and B are independent in case the probability of A, B is equal to probability of A times probability of B. If the set of events are more, we say that they are independent if probability of AIs, intersection of all AIs, is equal to multiplications of the probabilities of A. This is the formula that I have mentioned. So I mentioned the product and and intersections are the same. Here, we don't have always this. If you remember, we had this summation and union, and so that if these AIs are disjoint, then we have this equality. Here, we say that if they are independent, we have. Disjoint was easy because that's like two sets are disjoint if they don't have any intersection. Independence is not easy, actually, and you need to always you need to compute this one and make sure that this probability is correct. Even the people who worked a lot in the field, they may make a mistake that something are independent, so we can use this formula, and how these are not independent. And if they are not independent, means they are correlated. And again, as if you remember, we talk about correlation. So that if actually correlation is a good thing because you can use it to get the essentially learn. So all essentially ML machine learning is based on correlation. That from some data, some training data, you will learn the correlation. For those that you don't have the data, then you can infer the results. Good. So let's see an example. Say we say that two events A and B are independent. In case probability of AB is equal to this one, and this is for larger number of AIs. So consider this drug test. This is some experiment that is done. And so these are 4,000 people, and we have done some essentially two events have happened. One is that whether this person, is a woman or not. That's one thing. The other thing is that whether it tried essentially some drugs on them, and whether this drug fails or not. Good. So this is the table that we have it. Now the question is that will event A be independent from event B? Good. So let's write probability of A. What is probability of A? Probability of A is, how many people are A? A patient is woman. What is the probability of A? It's 50% essentially, or half, because half of these people are 2,000 people out of, so that would be equal to 2,000 over 4,000. What about probability of B? Probability of B is also how many people drug fails. If you see that here, it would be again 2,000. 2,000 over 4,000 would be again half. Now, what about probability of A? Probability of AB, you need to use this formula. So it is equal to probability of AB. First here, what is the AB? It means that it is that A intersection B, means that that person is a woman and the drug fails. So in that case, would be this 1,800 over what? Over 4,000, which is 9 over 20. Good. Now, whether A and B are independent, we should see whether probability of AB is equal to probability of A times probability of B. Of course, it is not. So it means that A and B are not independent. So what is the idea essentially? It means that, when these two are not independent, is that if you know something about this event, you can then the probability of the other event can change because they have somehow correlated. Again, this is intuition. The only way that you can mathematically you can get it is through this formula. You just compute it and then do it. An interesting example. So let's see a particular experiment that we are tossing a coin twice. The original experience that is. A is HT, head, tail, and head. B is just HT. Will event A independent from event B? Let's do the computation. What is the probability of A? So probability of A is 2 out of 4. So it is 2 out of 4, which is 1/2. What is the probability of B? Probability of B is 1 out of 4, because HT over this, which is 1/4. What is about probability AB? So A and B here, they have an intersection. So it would be essentially HT, and HT is happening with probability 1/4. Now, if 1/2 times 1/2 is equal to 1/2, 1/2 times 1/4 is equal to 1/4? No. So it means that A and B are not independent. Now consider this other case. B is equal to HT and B is equal to TH. Will event A independent from event B? So what is the probability of A? Probability of A again, 1 out of 4. So probability of A is equal to 1 out of 4. What about probability of B? Again, 1 out of 4. What about the probability of AB? Is A intersection B? It would be empty set A and B intersection of them, so that would be 0. And we are using axiom 2 here. So that would be 0. Is it the case that 1/4 times 1/4 is equal to 0? No. So it means that A and B are not independent. Now, why this example is important? You see, here we have this one. A and B here, they were not disjoint. They had an intersection, correct? As I mentioned, they are disjoint if there is no intersection. Somehow we say distinct. Distinct means not equal. Disjoint means there is no intersection. So in this case, these guys they were not disjoint. They had an intersection, and A and B were not independent. Here, in this case, A and B were disjoint. But still, event A is not independent. So essentially means disjointness does not mean independence. And why is it important? If you remember the original formula that we had here, so here we have this formula. As I mentioned, if they are disjoint events, then we have this property. But here we say disjointness and independence are two different things. None of them implies the other. Another thing, the transitivity. Transitivity means if A is independent of B and B is independent of C. Whether so A versus B and B versus C. Note that if A is not independent of B, B is not independent of A. Or if A is correlated to B, B is correlated to A. So it is symmetric. This is called symmetricity. But what about transitivity? A and B are independent. B and C are independent. Can we say A and C are independent? And the answer is not necessarily. Why? Consider essentially C to be equal to A. Good. So here A and B are independent. B and A are independent. But what about A and A? So in this case, so we should have it. What is the probability of? So what is the probability of A intersection A would be probability of A. So that should be equal to probability of A times probability of. So here this A comes in A intersection. Good. So this equality, we have only if probability of A is equal to 1 or 0. If 1, it is equal, 0 equal, otherwise they are not. So it means that these two events are not necessarily. So it means that unless A is empty set or A is F, the whole sample space, then we don't have this property. So it means that essentially this transitivity is not correct. And again, these are some of the important things. Symmetricity, it means that if A is independent of B, then B is independent of A, which is correct. But transitivity means that A is independent from B, B is independent from C. A and C, they can be independent or they cannot be. Another thing which is very important is conditioning. If A and B are events with probability of A is greater than 0, then the conditional probability of B given A is this formula. Probability of B conditioned on A is equal to probability of AB. Again, AB means A intersection B over probability of A. Good. So let's see an example. Consider a drug test. And then we have woman, men, success, and failure according to this table. So here, A essentially means patient is a woman, B means drug fails, and we want to compute these two probabilities. B conditioned on A and A conditioned on B. We need to use this formula. So let's compute the first one. So probability of B conditioned on A would be probability of B. So we need to compute this. Probability of B conditioned on A would be probability of A intersection B. What is the probability of A intersection B here? Means that the person is a woman and the drug fails would be 1800. What is the probability of A? Probability of A means that the patient is a woman. So it is 2,000. Essentially, it means, sorry, this means 18,000 over 4,000. This one means 2,000 over 4,000. This 4,000 will cancel out. It would be 18 over 20 or 9 over. What about probability of A conditioned on B? So in this case, again, so probability of AB still would be the same. Probability of A and probability of B, both of them are half, as we discussed. So the same equal things we have 9 over 10. Another interesting thing, if A is independent from B, what is the relation between probability of A intersection B and probability of A? And of course, if probability of A is greater than 0. Good. So if A and B are independent, then in this case, then probability of AB would be equal to probability of A times probability of B over probability of A. Correct? Because of the independence. So we can just cancel out these two. So that would be equal to probability of B. Or here we have, I have written it the reverse. So we say A, here we had B conditioned on A, we got a probability of B. Here we have probability of A conditioned on B, then we get probability of B. Yes? Sorry, give me 1 second. Good. So we have that one. This is conditional independence. So we can combine actually this one. We say events A and B are conditionally independent if probability of AB intersection, the condition on C is equal to probability of A condition on C times probability of B condition on C. And if these are events are more than 2, also you can have this one. The probability of this essentially intersection of AI's conditioned on C is equal to product of probability of AI conditions. By the way, this formula was also important. I think, what is the intuition on that? When we say that probability of A conditioned on B is equal to probability of A, it means that the fact that we know that B happened did not change the probability of A. And that's exactly the meaning of independence. So that's essentially so that you knew that something about B, but that does not change the probability of A. It means that these two are independent. So let's see some examples about conditional independence. So consider there are 3 events A, B, and C, and these are the probabilities that are defined. Probability of A is equal to probability of B, probability of C is equal to 1 over 5. And as I mentioned, these are just some numbers that we need to assign. Probability of AC means A intersection C is equal to probability of BC 1 over 25, probability of AB is 1 over 10, and probability of ABC is equal to 1 over 125. So the first question, whether A and B are independent or not. So what is probability of A is 1 over 5. What is the probability of B is 1 over 5. And what is the probability of intersection B is 1 over 10. So these are not essentially equal. So it means that A and B are not independent. But let's see, consider the case that whether A and B are conditionally independent given C. Let's write the formula. What is the probability of A conditioned on C? It is equal to probability of A intersection C, which is 1 over 25 over probability of C, which is 1 over 5. So in that case, would be 1 over 5. Similarly, probability of B conditioned on C would be the same thing, 1 over 5. What about the probability of AB conditioned on C? It is equal to probability of ABC, which is 1 over 125, over probability of C, which is 1 over 5. So that would be 1 over 25, which is equal to probability of A conditioned on C times probability of B conditioned on C. So what's the meaning of that? It means that A and B are independent, doesn't mean that A and B are conditionally independent. in some sense, when you condition on something, then I mean, it might be the case. What is the intuition is that A and B somehow they were dependent or correlated. But if you know that when you conditioned on C, it means that the area that they were intersecting, they were essentially correlating, does not show up. In that case, it means that in the rest of the cases, they are independent. That's essentially the meaning of this thing. That when you conditioned on C, then they are independent. Other thing that we want to talk about is Bayes rule, which is very important. Especially this is something in the something that will be useful for applications like testing, A/B testing, that we try to consider two events. That generally happens that, I mean, you have a website, you are creating a new website, you are sending part of the traffic there, and you want to make sure that everything works well. And this kind of, I mean, Bayes rules are very important, because if you know that what would be the, whether these new things would be a good website or not, then you don't need to spend a lot of money, because if you are sending these people, the traffic means money. And if even you send, I mean, you need to send a good amount of traffic such that you see some meaningful events. And if you see that these events that are going there, it may suck the new website, then it means that you are losing money. So you should not have done that. So it would be better to compute this kind of A/B, so to essentially compute this probability before running the experiment itself. I think let's take a 15-minute break. We will come and we will come back and continue. Great. Okay. So we talk about Bayes rules, and as I mentioned, so here, as I mentioned, you may do some A/B testing. There is some traffic that you want to send it. It's better to do the math beforehand instead of spending millions of dollars possibly and waste a lot of money and you don't get the result that you want. So there are two events A and B, and suppose the probability of, I think here is the probability of B is greater than 0 actually. Then we say that the probability of A conditioned on B is equal to probability of AB over probability of B. But then you can actually write the same way. Instead of probability of AB, you can write it. It is equal to probability of B conditioned on A times probability of A. We are just using the same formula here. Good. Now, okay, so why do we make things complicated? Because it might be the case that we know what is the, so to compute the probability of A conditioned on B, so we want to see whether people click more conditioned on the fact that we have a new website. Then you may not know this one and you don't want to spend money, but you may have some other prior information that can be used such that you can get this information. For example, it might be the case that you know probability of B conditioned on A, probability of A, and probability of B. These things, it is called inference, that we are deriving unknown probabilities from known ones. Here, probability of A, it is called, or probability of B is called probability before any evidence. This is prior. There is a likelihood. What is the likelihood? Is the probability of B conditioned on A. It means assuming A, how likely is the evidence? Good. And here, so this is the likelihood that we have it from some other information. And then posterior. Posterior essentially means conditional probability after knowing the evidence. And again, after knowing evidence essentially means that you are essentially putting a new website, you are sending the traffic there, and then you will get the result. The question is that can we use some of this probability from known information from past history such that we don't need to run the whole things and we have some ideas whether it is a good website or not. And these are the website, by the way, these are the some of the slides which you can use it for, I mean, like if you want to go for an interview, etc. That's a very good one because this is some basics of probability. theory that you can just go through them and then just remind you about all important aspects or crash course on probability theory. Let's see an example. This is actually a very good example that I have actually tested myself on that once a while to make sure that I remember, because you may easily forget this. So this is called inference with Bayes rule. And this is the example. So there is a bag. There are two envelopes there. One has a red ball, which worth $100. It's a black ball, which worth $0. The other one has two black balls. Black balls worth nothing. Then what do you do? This is like essentially it's the bag. You will put your hand in one of them. Hopefully it's not a snake. It's just the bags there. You will go there, you get one of these envelopes, then you open it, and then you bring one ball out. It is a black ball. Good. Then the question is that, and then you can take this envelope that you take out, or you can switch. The question is that whether you should switch or not switch. Good. So how many people say that we should switch? How many people say that we should not switch? So I think you should decide about one of them. This is the option. That is no other option of. I think the other people probably just leave after that. They don't do anything. But we need to do the math. Before that, we cannot do that. Okay, let's define E to be envelope, which is 1 means RB, means red and black, and 2 means black. B is the event of drawing a black ball. Good. Here, the probability of E conditioned on B is equal to probability of B conditioned on E times probability of E over probability of B. So that's essentially the Bayes rule that we are mentioning. However, here E by itself does not mean anything. So we should say, for example, E is equal to 1. Then here we should put it equal to 1, probability of equal to 1, or put it equal to 2 and so on. Let's compute this one for both of these probabilities. See which one essentially is the higher one, and then we go according to that. So what's the meaning of that? We want to compute probability of E equal to 1 conditioned on B. B means that we are the event of drawing a black ball. That happened essentially. Versus probability of E equal to 2 conditioned on B, means that we draw black ball. And of course, we want to see like this one, this envelope that we have, it is A is like essentially 1 or 2. Let's compute probability of B condition, or so we want to compute both of them. Here, of course, we need to compute it. Let's use our history. What is the probability of B conditioned on equal to 1? What's the meaning of that? So if E is the first envelope, what is the chance that we will bring essentially a black ball out of it? Would be 1/2, because essentially from one of these guys we got this one. Yes. So this is the case that if this happens, then I mean equal to 1, there is one of them is black, so there's a 1/2 probability that we will get one of them out. What about the probability that B but conditioned on equal to 2? In this case, be both of them black. So if you bring 1, the probability 1 will be black. So note that that's the thing, that when you reverse it, you have much better understanding about it. What is the probability that E equal to 1? I mean, you took one of these at random. You didn't see that. It would be 1/2. What is the probability equal to 2? The same thing, 1/2. What about the probability of B? Probability of B, essentially, you don't need it because both of them would be over probability of B, but let's compute probability of B as an exercise as well. What is the event that you will bring this ball at random and it is black? So you know that there are four balls, 3 of them are black. So and you have done a random things. You have chosen one of these at random, and then from one of them you chose one of them at random. You brought. So the probability that one of these comes black would be 3/4. Now let's compute it. What is the probability of E equal to B conditioned on B? That would be equal to probability of B conditioned on equal to 1, which is 0.5, times probability of E equal to 1, which is 0.5, times probability of B, which is 3/4. This would be essentially, this would be 1/4 over 3/4, which would be equal to 1/3. What about the probability of E equal to 2 conditioned on B? The same calculations, you are doing that. The only thing is that you need to change probability of E equal to, yeah, this one we need to put it. So this, in this case, would be probability of B conditional equal to 2, which would be 1, times probability of E equal to 2, which is half, times probability of B, which is 3/4. So this would be equal to essentially 1/4. I can write it 2/4 over 3/4. And then you will cancel out, and then it would be 2/3. So you see, this is exactly this, from the past history and the information, we could compute something. And this is the money, of course. It is important that, I mean, you compute it because you can get potentially $100. This is some kind of lottery. And if you do smart things, then essentially after, so when you see the black ball, it means that the probability that this guy is 1, the good one, is less than the probability that it be a bad one. It means that you should switch. Again, and this is important. Some people may come to me and say, okay, what about if I run this and the black, as actually I'm losing the money, because if I take the same one, then the red one is there. Yes, you can do that. You may even win a lottery. But generally, you will lose in a lottery. So here, it means that if you run this, yes, in one instance, you may actually switch and you lose them because you have done wrong. Because this is probability. It is not a deterministic thing. However, if you run this experiment, I don't know, 9 times, if you switch probably 6 of the time, you will win 3 times, like 3 times you may lose. So it means that if you repeat several times, that's the whole idea of probability. If you repeat several times, then you will get essentially the benefit. But in one instance, you may do it, and then you cannot come and say, blame, okay, you told me that I should switch. I switched and lost $100. No, there is no guarantee. Everything is probability. We just say that because this is larger than that, it's better to switch, but it means that, but it shows if you iterate something several times, then it shows. There's another one. It is a Bayes rule, which is a more complicated version. Suppose that B1, B2, and BK form a partition of S. Partition means that they don't have any intersection and their union is equal to S. Then assuming that the probability of B is greater than 0 and probability of A is greater than 0, then we have probability of BI conditioned on A is equal to probability of A conditioned on BI times probability of BI times probability of A. So far, the regular Bayes. Then I will replace the denominator by the formula that I have mentioned at the earlier class. Because A intersection BJ, this would be disjoint. So if I do that, I can, instead of taking the union of them, I can write, and A essentially would be union of this A, BJ. So instead of the union, I can write the probability, I can write some of the individual probabilities. Now for each of them, I will just use the Bayes rule again. So I will write it probability of, I will write this one probability of BJ times probability of A condition on BJ. So why we are making this so complicated? Because essentially this may happen. The same Bayes rule, if we have this B1, B2, maybe it's not just between one website, but between two websites that you want. Then in this case, whenever you want to get the probability of BI conditioned on A, you will consider that one for this particular BIs over all such possibilities, sum of all these possibilities. In some sense, this is a normalized version of that. So you normalize this probability over sum of all possibilities. And again, this is correct if we have this partition of them. If there's not the partition, then we don't have this property. And this is a formula that is useful. You can see some applications of that. And these are some of the things, again, in top companies. If you want to interview, if you interview, have an interview there, it is very typical that they may ask some probability, because this probability is very important. A/B testing is huge in lots of these companies, I don't know, Uber, Google, etc. Everything is very important. And it is important that if you run something, this you can make a good judgment of it or save money for the company. And probability is super important. And again, these are some of the slides that you can take a look at it, but from this you can also see more similar problems that you can maybe do more exercise such that you can do it. And more importantly, again, these are some of the things that ChatGPT cannot do it essentially. Like this formula that I have mentioned, the switch or not switch. Sometimes if it has written exactly this form on the web, it can find it. But slightly change the statement and ask it, it will not do that. I think that would be a good exercise. You can try, see whether it can give you the solution or not. And again, 5 years from now, I don't know, but at the current moment, you are in a much better situation if you know this basic stuff, and because you are better than ChatGPT, and they like you better than ChatGPT for their purpose. Good. Let's talk about random variables and probability distribution. That is also important. So a random variable X is a numerical outcome of a random experiment. So you are doing some random experiments and some number is coming. The distribution of a random variable is a collection of possible outcomes along with their probabilities. But distribution, how can we represent essentially a distribution, especially in the discrete case? For each of them, X equal to a particular X, what is the probability of that? And theta here means the name of the distribution. Theta is the name of distribution. So a question, how can we represent a distribution, especially a discrete one? We can actually have a list, for example, in Python, or an array, or like essentially a mapping, for example, in C++. And then for each X, say this is X equal to 1, 2, 3, 4, I don't know, n. What is the probability of each of them? And this is important. Sum of this probability is equal to what? 1. That's the main thing. So in the array, it is equal to 1. In the continuous case, we are considering some time as well. Then you need to take integration to get it. In the continuous case, we cannot say probability of X equal to X, because always it would be 0. You need to take equations. You need to take integrations. We work more with a discrete case. The support of a discrete distribution is a set of all X for which probability of X is greater than 0. That is called the support of the distribution. Like, support means the important part of a distribution. Finally, last but not least, the joint distribution, which is very related to joint probability of two random variables X and Y, is the collection of all possible outcomes that it can happen for X and Y together with their corresponding probabilities. For example, it might be so you can have all values of essentially X here and Y here. This is 1, 2, 3, 1, 2, 3. And then here, you will say what's the chance that X is equal to 2 and Y is equal to 2. This is essentially, this means and of them. This is intersection. The catch. Then the sum of the probabilities over the whole table is equal to 1. Not each row or each column. The whole thing, so our whole table, the sum of the probabilities would be 1. Because when you consider joint probability, you know that something happens for X, something happens for Y, and then overall, you are in one of these cells. So that's essentially the whole thing that you can get the probability. Let's see an example. You have a set of sequence of 3 rolls of a die. Let X be the number of dots on the 3 rolls. Good. What are the possible values for X? So the possible values for X, it can be X equal to 3 at least, because one of them should be 1. So it would be between 3 to 18. 18 means all of them are 6. What is the probability that X is equal to 3? Is that the first one is 1, the second one is 1, and the third one is 1. The probability 1 over 6, 1 over 6, 1 over 6, so it would be 1 over... And these are independent. That's the reason that we can multiply them. Otherwise, we couldn't. So 1 over 216. But what about the chance that is X equal to 5? We need to consider all possibilities. So one possibility is that you have 3, 1, 1, then you have 1, 3, 1, or you have 1, 1, 3. So there are 3 of them that they become 5. Are these all possibilities? No, because we can have also 2 to 1, 2, 1, 2, and 1, 2, 2. So there are 6 cases, and each of them is again 1 over 216. So it would be 6 over 116. Expectation. That is very important. For a random variable X coming from this distribution, that's the notation that we say that X comes from this probability distribution. And as I mentioned, probability distribution, if it is just essentially for a variable X, discrete case, we can write it as an array or list or mapping. If it is like for X and Y, then it would be an essentially 2-dimensional array or a matrix. Or if for 3 variables would be 3-dimensional arrays. We will talk about NumPy stuff that they can represent this, for example. So for a random variable X, the expectation is X times probability of X is equal. So essentially it is X times that. So in an empirical sample maybe, essentially means that, you will take a regular sample, then all the probabilities would be equal. So in that case, you can bring, all of them would be 1 over n, so you can just bring this one out of the equations, and it would be 1 over n. Continuous case. For the continuous case, you need to do the integration. Again, the same formula, minus infinity to infinity, X times probability of, this is the name of the distribution, P of X. So in a discrete case, you can say expectation is just the average of the numbers in the support, because all others are 0, weighted by their probabilities. So in some sense, it's a weighted average. And what are the weights? The probabilities. A very important fact about expectation is that we have linearity of expectation. It means that expectation of x1 plus x2 is equal to E of x1 plus E of x2. That's very important. We are using it a lot. Let's see an example here. Let S be set of all sequence of 3 rolls of a die, the same instant. Let X be the sum of the numbers of the dots on the 3 rolls. What is E of X? What expectation? So again, these are the 3 dots that you have it. And you want to see what is the expectation. To do that, let's do the formula. This is the thing that you need to, again, be very familiar with the basic stuff. To do that, we can define, so this is X, sum of these 3 variables. We can say X is equal to x1 plus x2 plus x3. What is x1, x2, x3? Is that essentially the number on each die. The first one, the second one, and the third. Good? So then I can use the linearity of, so X is equal to, then I can use the linearity of expectation to write E of this is equal to E of this plus E of this plus E of this. Here I'm using the fact that x1, x2, and x3, these are the same events. because it's a just. So expectation of x1, x2, and x2, x3 would be the same. So that would be 3 times expectation of x1. Now, what is the expectation of x1? So all of them have the same probability. So this is the empirical case. The number can be between 1 and 6. So it would be sum of essentially average of 1, 2, 3, 4, 5, 6. What is the average? So we know that the number, if you have the numbers from 1 to n, then the sum of them would be equal to n times n plus 1 over 2. So I have 1 to 6. So then the sum of them would be 6 times 6 plus 1, which is 7 over 2. So it would be 3.5. So it means that this would be 3 times 3.5, which is actually equal to n over half. Now, what about if say that the same instance consider it, but here x is the product of the number of dots in this. Here we don't have linearity of product. So you need to think about it. Of course, one way that you compute all possible cases. So this is always we can do that. You want to get E of x, consider all possible events that can happen, like the one that we got it, for example, for 5, like 1, 1, 3, and so all possible things. What is the essentially probability of each of them? And then in this case, what is the sum? And then compute it. But that would be maybe too cumbersome. You can think about some way, and this is actually some good exercise. You should think about it. You may use this fact. You can search for it that if these events are independent, maybe we can multiply the product. But you should search, see whether this is correct or not, and think about it. So if these events, can I multiply or not? And under which condition I can? That you can actually, that is a good exercise. You can think about it, and like eventually you can think about. Another very important thing is variance. So variance of a random variable x is the expectation of x minus e of x to the 2. And standard deviations, sigma, is square root of variance. Here we have is expectation of that. But if it was not expectation, you can think about somehow variance is x minus e of x. Sorry, a standard deviation, sigma. But of course, it's a bit different. But in some sense, it says that how much we are concentrated around the mean. How much we are concentration against, like, for the expectation. It means that, like, if you run this one, how far can we? Yes, we know the expectation is this, but you might be very far from this essentially. This one tells you how much you are concentrated around this. So, and again, variance or sigma is very important. Again, these are some of the things that we are using it. For example, if you are using it, these are some of the things that are used in the A/B testing. It is called t-test, for example, f-test. F-test variance becomes important. Or I think S-test, that was another one. But these are some of these tests that you want to see whether after an experiment, whether actually this information that you got, whether it was because of noise or it was some meaningful information. Again, these are very useful in A/B testing. And I mentioned A/B testing to see whether this is a new website, whether it is better than the website or not yet. So these parameters become very important. So let's do the computation. Variance of x is equal to e of x minus e of x to the 2. Then I will just essentially write this one, the expansion of that. I have written it. X to the 2 plus e of x to the 2 minus 2 of x e of x. One important thing. What is the expectation of a constant number? Expectation of a constant number is just the number itself. So what's the meaning of that? And it is important. E of x is a constant number, is not a variable. So expectation of x is not a, so x is a variable, but E of x is not a variable, it's just a constant. So E of x is equal to what? Equal to E of x. Because of the previous one, because that was equal to C. Expectation of expectation would be equal to just expectation. So now using this formula, so and linearity of expectation. So E of x to the 2 would be E of x to the 2. This is linearity of expectation. But if the expectation of expectation to the 2 would be just the expectation to the 2, because it's a constant. Finally, we have 2 minus 2x E of x. So here, minus 2 E of x is a constant. That will come out of the expectation. So it would be minus 2 E of x. What is remaining would be just E of x. This is equal to minus 2 E of x to the 2, correct? So this would be E of x to the 2. This is plus, this is plus, this is minus 2. It would be minus E of x to the 2. That's the formula for values. And again, it is very useful in some of this, especially about F-test. Research some of this test. You can read more from them, essentially. Unfortunately, for them, I don't have the videos. So you can ask ChatGPT. Good. So let's see some famous distributions. Bernoulli distribution. So this is the outcome of an experiment. Can be either success or failure. So either 1 or 0. The probability of success is P. The probability of failure is 1 minus P. You can consider essentially you have a bias point that this probability P becomes head, this probability 1 minus P becomes a tail. What is the probability of, I mean, this is a distribution theta. What is the P of x? It is equal to P to the x times 1 minus P to the 1 minus x. Let's see why. So if put x equal to 0, what is the probability of x is equal to 0? It would be P of x to the 0 would be 0, would be 1 times 1 minus P to the 1 minus x, which would be 1, essentially would be 1 minus P, the same thing that we had. If you put x equal to 1 here, then in this case would be P to the x would be P to the 1 times 1 minus P to the 1 minus 1, which would be 0. So it would be P. So what is the expectation of this? Expectation is simple because it is just P times 1 plus 0 times 1 minus P. So it would be P. What is the variance, the formula? E of x to the 2 minus E of x to the 2, which is this. So E of x to the 2 is equal to, so E of x to the 2 is actually, it is equal to E of x. Why? Because if x is failure, 0 to the 0 would be 0. If x is success, 1 to the 1 would be equal to 1. And then the probabilities would be still the same, would be the 1 minus P and P. So E of x to the 2 is equal to E of x. So what is E of x is P. So that would be essentially E of, so this would be equal to E of x minus E of x to the 2, which is equal to P minus P to the 2, which is equal to P times 1 minus P. Good. Another famous one is the binomial distribution. So here when we have n rows of a Bernoulli distribution, so x is equal to sum of n variables that each of them is a Bernoulli distribution, and we are representing it by essentially binomial bin of p, the probability, and n is a number. So you can think about it essentially you have a bias point that you are essentially tossing it n times. And you want to see how many times you get head versus how many times you get tail. So here the random variable x, as I mentioned, stands for the number of times the experiments are successful. And this is the formula. Again, you can put these numbers there and you will see why we have such a formula. What is the expectation of x? Expectation of x, you can just use the linearity of expectations. Because this is each of them is a Bernoulli, and we knew that E of xi is equal to P for Bernoulli. So it is n times P, because you are just summing up P n times. What about the variance? It is np times 1 minus p. I mean, of course, you can do it from this, but we can do it in a better way that we will explain. So let's go to the normal or Gaussian distribution, which is, so the Gaussian distribution, you represent with two things, mu or mu and sigma to the two, variance. So essentially expectations and values. This is the formula for that, is a bit complicated. But what is the shape of a distribution? Normal distributions are essentially some distributions like this, that this is the mean of that, or this is mu, and this is essentially the sigma to the 2 is the variance of this. It's depending on mu and sigma, then you can see what is the shape of it. So it can be the shape, it can have a heavy tail like this, or it can be very, light tail, or something like this. But these two parameters exactly decide what would be the shape of this. So for normal or Gaussian distribution, we know that the expectation, of course, mu, and the variance is sigma to the 2. Important, if x1 is from these normal distributions and x2 is from these normal distributions, then, of course, if you have considered a variable x equal to x1 plus x2, then this one, we have the linearity of expectation always. So we have the new mu would be mu1 plus mu2. But here we have also linearity of variance for normal distribution. So we don't have linearity of variance in general, but we have linearity of variance for normal distributions. Now, this is important. Binomial distributions are indeed normal or Gaussian distributions. If you see the shape of them, essentially according to the P and N, this is the binomial distribution. This is a binomial. All of them are normal distributions. Good. Now let's go back to the exercise that we had here. So variance of x, because essentially this also Bernoulli thinks is a Gaussian or normal, because x is the sum of the n normal variable, essentially normal distributions. We have linearity of variance as well. If you remember, here the variance was p times 1 minus p. Here we have n variables here, so it would be n times p times. And normal distributions or Gaussians are very important. This is a very typical thing. It is kind of symmetric distributions that happens in lots of experiments. And this assumption that this one, so it's a very general distribution that the people consider it and accept it. Not all the time is like that, but lots of times these normal things come to the play. And as I mentioned, this is the shape of it. Finally, last but not least, another normal distribution is Poisson distribution. So it comes from binomial distributions. The main property of that is that the expectation and variance of this would be the same. So essentially, it is you are fixing the expectation lambda, and then let the number of trials goes to n to the infinity. A binomial distribution in this case, it becomes a Poisson distribution. The formula for that is this formula. But the main important property for that is E of x equal to lambda and variance of x is equal to lambda. One important property of this is for Poisson, they are talking about it is the memoriness. It doesn't care that, whether this event happens before or not, essentially. You can read more about it from ChatGPT, etc. But this is also very important for lots of queuing theory that the people are using a lot for Poisson distribution. These are some of the things that you can these are some famous distributions that you should know about. Good. Now, knowing these distributions, one question is that how can we use them essentially in Python? So this is the experiment. This is something that I want to go through that. So first, we are using here from Colab. Colab.research. Okay, that I mentioned. Everyone can go there if you have a Gmail account. Then you have such a thing, and this is a Jupyter notebook environment, and that allows you to do processing, etc. Then, so just you can go there and then you can essentially write any Python thing. So you don't need to have any compiler. Even if you use your cell phone, you can use that. So here we are importing NumPy as MP. Essentially, this is a typical thing that in Python we are using it. This is the class or the package that has NumPy. We use it as MP. One thing which is important, NumPy.random. That is the one that lots of random stuff are there that we are talking about. And the other one is SciPy stat. These two are important. This one is RM and this one is stat. And we are talking more about this one later, but this is a very good library that you can do lots of stuff in Python. So here, first, then we have from NumPy this function full. That creates an array of size full 4 3 means that create an array of size 4. Each of them is 3. Good. And you see, we say that print A1, and it has printed. Now, this is interesting. So here we say that X is equal to 1000 RM of rand n 20. How many of you use rand n? Rand n means essentially a random, which is a normal distribution. Now, rand n, what is the, so this is the normal distribution that we talk. So what is the mu of rand n? The expectation of that by default is 0. What is the variance of that? 1. Now, what does this one say? It says that rand 20 means that generate essentially rand n with an array of size 20. So it generates an array of size 20. And then what does it mean that 100 times this? 1000 this. In this case, if you, so 1000 means just essentially multiply this 1000. But when you multiply 1000, actually this, the mu does not change because it was 0. 1000 times 0 would be the same essentially. But what about the variance? The variance would be essentially because this is a normal distribution, it will be multiplied. So essentially you get these arrays of size 20 that from a normal distribution such that its variance is 1000 and this mu is 0. Then you will add 10,000 to that. So you just change the median of the expectation of that by 10,000. So here essentially is this is generate essentially n random numbers from a normal n samples. Here 20 samples from a distribution, normal distributions with variance 1000 and essentially expectation 10,000. And this, if you print it, that would be like this. Another one here is RM, rand int. Rand int is just generating some random numbers for you that they are integers. Here we say the size of the array is 20, and we say rand int between 0 and 2. Here the interval is 0 and 2, but this is essentially this, it would be not including the last guy. So it would be only 0 or 1. And it's a random. So it means that with probability half would be 0, with probability 1 would be 1. So that is the one that we have printed. Now, so this is the thing that we have done. So I define d1x, d2x, and then I'm using some of this stat one. This one, there are the Pearson and Spearman. These are two famous things to get the correlation between two vectors. Why the correlation is important? If you remember, we discussed that correlation is everything. that we talk about causation, cause correlation. And correlation is the one that actually it's used a lot at machine learning. So when you train a data, so this is X and Y. For part of the data, you will train it. What's the meaning of that? It means that here you try to find a correlation between X and Y. And X might be not just one dimension, it may have several dimensions. You will find a correlation here. Now for the rest of it, this is for the train. Now for the test one, here you have only X's, but for Y's, you don't have the things essentially. Good. So here, essentially, here you will learn from this in the training part, you will learn this data and you learn the correlation, and then in the test, you are using this correlation to fill in the table. For example, as I mentioned, you can give such a table to Amazon AutoGluon, and it fills these guys based on the correlation. So here, when you get these two correlations, if this X and Y is completely correlated, then you will get essentially factor 1. Essentially means that if X this is essentially, it means that Y is just some linear function of X, and then you get a correlation. If it is the reverse, like X is a minus of X, essentially, you get correlation -1. Anything in between, you will get between -1 to 1. Zero generally means they are independent, or no correlation. So this correlation is very important because this is some of the data science. So you get some data, and this is a typical example that they may give it to you that say, okay, go and generate two things and see whether they are correlated. And as I mentioned, if they are correlated, then you can, from the fact that these are, if there are some initial data you have it, then for the rest you can figure it out what would be the question mark. You can fill in this table. These are, as I mentioned, Pearson and Spearman. You can actually search. These are two important things for getting the correlations. But that's the whole meaning of correlation. It means that if they are completely, one is the linear transformation of the other, would be correlated, completely correlated, and then it would be 1 or -1, depending on whether it's 1 is. So essentially, absolute value is the one that it is important. Absolute value of the correlation. If it is high, means that they are very correlated. And if you have some information about X, then from that part, you know, you can say what is the corresponding one. So here, in this case, we have computed this. It was a little bit correlated, not much, essentially. It's almost 0 because both of them are some kind of distribution that was generated independently. Anyhow, and you can read from Pearson and Spearman essentially using ChatGPT or on the web. Good. So this is the website. I think you should go and try to know about this kind of NumPy random, and especially SciPy stats. These are something which are very useful. And this is, again, a typical thing that may happen in an interview, especially for high level, because those that they know exactly that, like Facebook, you will do some A/B testing. A little bit of mistake there, it would be millions of dollars. Would be more than your salary, probably. I don't know. Whole like 10-year salary, you may lose essentially if something is not done correctly. So for them, it is very important that you are very strong in these things and you know, understand probability. Then you do A/B testing, you will understand this. So these are very basic things that you know that. And this was a crash course on that probability and something that you can use it in Python. Good. Great. And next time we talk about linear programming, this is very important. Again, something that has been used. I have used it essentially companies like Amazon or Overstock, and then I made this was like essentially like optimizing millions of dollars based on this. And we will talk about this. Very important. Not all people know about it, but this is very basic stuff. We have some assignments there, but you know that you have full power because this is somehow knowing that how you can optimize the problem essentially in a practical way. Not too many people know about it, but it is super important. Also, we will talk about, so one thing which is very important is pulp. That you should know about it. We will talk more next time. Something that can solve linear programming. Another thing, we talk about graphs and networks. Again, we talked briefly about them. You should be able to get very good knowledge about it from my YouTube videos on introduction to algorithm. We have several things about graphs. I think that I just strongly recommend that you will go and watch them. And one thing that we are using them would be the one that we are using graphs. Lots of these graph algorithms are already implemented, and you can use it is network X library. It's a very strong one. Almost anything about graphs has been implemented. How many of you have used network X? Yeah, that's a very good one essentially for graphs. There are maybe some newer version of that. I mean, like some more advanced version of that, but I think that is already a very good one. And we will talk about it, more about it, like in the next time. And and we will talk a little bit about basic other tools, like we are talking about this kind of GitHub, cloud computing, containers. We will give the high level. Again, more details you can always get it from ChatGPT and even implementation of that, because you can ask and you can get results from ChatGPT. Good. So I think I wanted. I will finish essentially at this moment, and then we will continue next time.